This chapter is titled Matter and Energy. So we've talked about matter, and now we're going to talk about energy. So energy is also a major component of our universe. Energy is not matter. It is something else. One way to define energy is the capacity to do work. Doesn't mean it actually does the work, but it's the capacity to do work. Well, then we need to know, well, what exactly is work? We think of work as a place you go to, right, where you do stuff that maybe you don't like and they give you money later, right? Okay, that's the societal definition of work. The science definition is work is the result of a force acting on a distance. So if I take this bin and I push it across the desk, I just did work. I applied a force across a distance, a force that moved the bin. That was work. So energy is the capacity to do something like that. We are not going to go very far into exactly what energy and work are. Physicists do a lot of stuff with that, and if you take more advanced chemistry classes, you'll learn a little bit more. We just have to learn enough to understand the chemistry we need. So the reason we have to talk about this at all is that the behavior of matter is driven by energy. And so we have to have some understanding of energy because it explains why matter does what it does. Why does butane burn when you have it in the presence of oxygen and you give it a spark? Why doesn't a lead bracelet do that? It has to do with energy. So just like matter is conserved, energy is also conserved. Energy is neither created nor destroyed. This is called the law of conservation of energy. The other one was the law of conservation of matter. Energy cannot be created out of nothing. It does not vanish into nothing. The total amount of energy in the universe is constant. Energy can be transformed from one kind into another, and it can be transferred from one object to another, but the total amount of energy remains constant. It can't be created or destroyed. It tends to transform from a more useful form into a less useful form. And so we'll sometimes, it appears that energy is lost. Well, it's lost to being useful, but it's still out there. It's just not useful anymore. So there are different forms of energy, and the two main distinctions are kinetic and potential. So these guys right here. So kinetic energy and potential energy, and the others are really subcategories. Kinetic energy is the energy associated with motion. There's a college major that's become very popular, kinesiology. Kinesis has to do with moving. Kinetic energy is the energy of motion. When something is moving, it has energy. Potential energy is energy associated with position or with composition. So if I take this dry erase marker and I hold it out at shoulder height, it has potential energy. Because if I let go, what's going to happen? It's going to fall. Yep, just like the pencil yesterday. When it fell, it started moving, didn't it? As it was moving, it had kinetic energy. So the potential energy of me holding it above the floor got transformed into kinetic energy. Now that it's sitting on the floor, it has less potential energy because it's hard to fall off the floor. Other types of energy include electrical energy. This has to do with the flow of electrical charge. Thermal energy is the energy of the random motions of atoms and molecules in matter. So thermal energy is a kind of kinetic energy. So if all of you guys started just like wiggling or chair dancing or something, right? The thermal energy in the room would go up because you're moving. Are you moving relative to each other? No, but you're moving more. There's thermal energy, a type of kinetic energy. And then there's chemical energy. Chemical energy is a form of potential energy, and it has to do with the positions of the particles that compose that chemical system. So butane will burn because of how the carbon and hydrogen atoms are arranged relative to each other. a lead brick will not burn because of how the lead atoms are associated with each other. It's energy. I thought I was going to say something else. Vanished. So the total energy of a sample of matter is its kinetic energy in all the different forms plus its potential energy. So the total amount of energy is the kinetic energy plus the potential energy. If we think about a reservoir here, the water held behind the dam has high potential energy. Because if you open the floodgate on that dam, what's going to happen? That water is going to pour out. Does rushing water have energy? Does it have the capacity to do work? Yeah, it can push cars right off of bridges. It can do all kinds of things, right? A lot of energy. When it's here, it's not really doing anything, but it has the potential to do stuff. It has potential energy. So here it has high potential energy. When we let it out, it has lower potential energy, but that high potential energy got transformed into kinetic energy. Well, if we're going to talk about energy, we have to be able to measure it. So the two common units that we'll encounter in this class are the joule, that's a J, the joule and the calorie. We'll be using both of them. A calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Some of the definitions of units seem a little strange. But if you think about it for a while, I dare you to come up with a nicer one. So how much energy, if you had a gram of water, it's at 25 degrees Celsius, you heat it up to 26 degrees Celsius. The amount of energy needed to do that is 1 calorie of energy. Now this calorie is different than the calories you count if you're on a diet. Those are nutritional calories. They have a capital C. Capital C calorie is larger, it's bigger than the lowercase c calorie. So capital C calorie, that's equivalent to 1,000 calories, the small ones, which is a kilocalorie. I will not try to trick you with this guy on a test, but I will warn you there's at least one problem, I forget if it's homework or worksheet, where yeah, it's going to try to trick you with that. And you'll get the wrong answer, you'll go, what the heck? Like, well, that capital C is important. That's a nutritional calorie, and it's the same as a kilocalorie. PG&E uses a different unit for energy called a kilowatt hour. These conversion factors here, I am not going to require you to know. Kilowatt hour might show up in a conversion problem, but other than that, we're really not going to use kilowatt hours in chemistry. We will be converting between calories and joules. 1 calorie is 4.184 joules. I'll give that to you on an exam. You don't have to memorize it. And this big C calorie is 1,000 of the little c calories. That will not show up on an exam, but just be aware for homework. So we can convert units using the method of dimensional analysis, just like we do between centimeters and inches or whatever. So here's the question. The complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? So we're just going to approach this as a unit conversion problem. There's only one number, so let's write it down. 512 CAL. The question tells us what we're looking for. How, that's the question word, how many kilojoules? So over here, I'm going to have kilojoules. This prefix, kilo, can be used with any unit. You could even use it with English units. People might not know what you're talking about, but you could do it. So kilojoules, kiloliters, kilometers, kiloseconds, kilobucks. You've heard of megabucks, right? Megabucks is literally $1 million. Mega means 1,000,000. Megabucks, $1,000,000. So if you see that K, it just means 10 to the third joules. So how do we get from calories to kilojoules? Well, we need some sort of a conversion factor. So look in the table. A lowercase c calorie is equal to 4.184 joules. Notice there's no kilojoules in here. It's okay. So let's write that down. 1 calorie equals 4.184 joules. So I found that one. That would allow me to convert calories to joules. Could I go from joules to kilojoules?
Yeah.
Sure. I just use the prefix. Whoops. Okay. So there's my path. If converting units and doing these sorts of problems is challenging to you, write down the path. Okay? I mean that. Write it down. People show me their work and they just started scribbling things. Where's your path? Oh, I didn't think I needed to write it down. If you're asking me a question, you needed to write down the path. So just write it down. 512 calories. We look at the path, it tells us what to do now. It's our notes. I see 2 arrows, I need 2 conversion factors. So times in a line, times in a line. Here I've got calories to joules to kilojoules, so that's what I write on the top. I've already got calories, and I'm going to put joules here, and I'm going to put kilojoules over there. I'm following a pattern. I need calories to go away, so I'm going to divide by calories in the next term. Calorie divided by calorie, anything divided by itself is 1. And then over here, I'm going to divide by joules, so the joules cancel out. I'm left with kilojoules, which is the unit I'm trying to find, so this is a good sign. Now I put the numbers in. Dimensional analysis, you do the units first, and then you stick the numbers in. So I found this relationship, and so I need to keep 1 with calorie. You can't switch them around. 1 calorie equals 4.184 joules. The reason I can multiply by this factor is that this factor is numerically equal to 1. The numerator, 4.184 joules, is equal to the denominator, 1 calorie. It's just a different name. You know, how old is your baby? Well, he's 36 months. Do you hate it when people say that? He's 3 years old. Just say 3 years. 3 years, 36 months. Same thing, right? 4.184 kilojoules, same thing as 1 calorie. What's on top has to be numerically equal to what's on the bottom. The numbers aren't going to be the same, though. Just like 36 months and 3 years, the numbers are different, but the length of time is the same. Over here, we have joules and joules, and then we have that kilo. Kilo means 10 to the third. I have kilo up here. I never put kilo with 10 to the third. I put the 10 to the third on the other side. 1 kilojoule is 1 times 10 to the third joules. And now you need your calculator. So when you do this in your calculator, start at the left, 512, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. It's the most straightforward way, and it'll get you the correct answer the most frequently. If you try to do something else, it may or may not work. But give my method a shot before you go on to your own crazy thing. Obviously, dividing by 1 doesn't change the answer. So you can skip multiplying and dividing by 1. But some people just need to do it all, and that's absolutely fine too. So 512 times 4.184, and then divided by, because I did divide by 1 times 1, and this number, you have to enter that correctly on your calculator, 1EE3. 1EE3 equals, and my calculator is showing me this. And the unit would be kilojoules. Do you get that number? If you got something a lot bigger, you're having issues with your EE button on your calculator. How many significant figures should that have? 3. Awesome. So 512 calories. That's a whole number, but calorie is a measure of energy. It's not something that can be counted. Obviously, but I count calories? Yeah. You think you're counting calories. They're not physical objects. 512, 3 sig figs. So then here we go. And our best answer is 2.14 kilojoules. Any questions? Yes?
The 12.184 and the 1 over 1,000 both don't have significant figures, right?
This relationship is exact.
Yeah.
This one, I'd have to look that up. It might be exact, but then again, maybe not. I don't remember. In this case, fortunately, it doesn't matter, right? Because this, even if we counted sig figs here, this would be 4, and that one's still less. So, but that's a good question. Is it exact because it's a conversion factor? No, not necessarily. Because the relationship between liters and gallons is a conversion factor, but it's not exact because it's between 2 different systems. And this between the joules and the calories, those are both the metric system, but that's a little iffy. Yeah, I don't honestly know the answer to that. But you cannot assume that conversions are exact just because they're conversion factors. If you look for conversion factors, you'll see them written with a different number of decimal places. Like that one between meters and miles and kilometers, 0.62 or 0.621 or 0.621, blah, 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 depending on where you find the conversion factor.